Archimedes. The city walls shook as enormous stones shredded enemy timber and ships listed like caught animals. He stood behind plans and pulleys and equations while the Romans pounded at the gates. What he built was not guesswork. He turned math into instant force. The basic idea was simple: store energy slowly and release it all at once. Torsion springs pulled back arms that threw heavy bolts and stones with terrible speed. That changed the fight. Sailors who expected slow siege engines found themselves facing machines that spat projectiles with surprising accuracy. Then there was the iron hand that toppled ships. A giant lever lowered a hooked arm onto an approaching vessel. Skilled crews hauled, and the ship lurched until buoyancy betrayed it, and the hull rolled. Modern engineers have used ancient materials to build a scale model. The mock ship tipped. The principle held. Stories about burning ships with mirrors followed. Ancient writers described sunlight focused into heat that ignited rigging. In 1973, a Greek experiment showed smoke and charring under perfect conditions. In 2005, engineers at a modern school managed to smolder a small model boat when the sun was sharp and the mirrors lined up precisely. Television teams later tried and failed in real-world breezes and wavering light. So what is the takeaway so far? The mechanical weapons are solid engineering. The heat stories sit on the border between myth and clever optics. The real shock is how quickly someone who understands these machines can rewrite what seemed impossible. And then there is the human cost. Men who record these designs risk being written out of comfortable histories. The next part explains the archaeological breadcrumbs and the evidence experts still argue about. The siege engines relied on stored force in twisted ropes and wooden frames. Bundles of sinew or hair were wound tight until they behaved like giant springs. Release the arm, and the stored energy snaps forward, launching a stone that can weigh up to 700 pounds. That is why range and accuracy suddenly became deadly. Builders tuned angles and release points so shots landed where they were meant to. The iron hand used leverage over the hull and the enemy crew. Lower a hooked arm, secure it, then pull with crews trained like a muscle. The lifted side lost stability and went over. Engineers in the modern era recreated the mechanism with period tools and proved a model ship could be rocked and tipped. The math and the mock-up agreed. The mirror stories sit on a different line. They require perfect calm and a mirror field aligned until heat concentrates on one point. Early experiments in 1973 produced smoke. A later experiment in 2005 caused smoldering under ideal conditions. Television teams tried at sea and failed when wind and waves scattered the focus. So the conclusion is mixed. Mechanical machines are believable. Focused sunlight is plausible but unreliable in real battle. What matters most is not whether every legend is true. It is that a mind trained in geometry and leverage could convert theory into battlefield change. It is also that the people who document these machines do not always survive history intact. Some names become shorthand for genius. Others fade. The physical machines leave scars. The human record is more fragile. Leonardo da Vinci. A single page of sketches looks like a war catalog. Gears mesh, cranks rotate, and tiny cannons point out like teeth. He did not build most of these machines. He drew how they would work, which, in that age, was almost the same thing as inventing them. One of his answers to slow reload times was a multi-barreled cannon with 33 tubes on a rotating frame. Line up the barrels, fire a volley, rotate the platform, fire again. The idea was to keep pressure on an enemy without waiting for reload. It reads like a blueprint for continuous fire. He also sketched an armored vehicle wrapped in a conical shell like a tortoise. Men would turn cranks inside, and the machine would roll forward with small cannon ports around its edge. It was not just armor. It was intimidation. Seeing a moving shell bristling with guns would have broken morale before the first shot landed. Then he drew a crossbow that spanned 27 yards. Its purpose was less practical than symbolic. A collapse of that scale would hurl massive stones and spread panic. He understood battlefield psychology as well as mechanics. These designs mix clever mechanics with theatrical thinking. Cranks, gears, and rotating mounts solve real problems. The giant ideas probe the limits of materials and manpower. Some inventions are plausible with late medieval technology. Others require resources or manufacturing power that did not exist in his time. What matters is how he thought. He treated force as a problem to be engineered. He mapped motion and then tested concepts on paper. Centuries later, engineers will build models based on these pages and find that some parts work better than expected. The designs show a mind that took the violent needs of war and translated them into clear mechanical steps. What followed would test whether his ideas were dreams or blueprints that could change battlefields forever. Across centuries, his pages became test beds for later hands. Model builders read the lines of pen and ink and tried to turn idea into motion. Cranks and gearing translated into working prototypes that moved and fired. Small-scale versions of the multi-barreled frame rotate and spit short volleys when loaded and timed correctly. The armored shell can be framed and pushed across a field in controlled tests. The giant crossbow can hurl a lump of stone if you have the timber and the draft power to pull it back. Not every sketch survives contact with metal and rope. Bearings wear. Human crews grow tired. Materials of the era would have limited size and rate of fire. In some cases, the plans require manufacturing that would have been rare in a 15th century workshop. That does not mean the ideas are useless. It means they chart a path. A single clever mechanism can lower the labor cost of a task or multiply the pressure on an enemy line. Modern reconstructions do two things. They validate which parts of the drawing are pure engineering and which are theatrical flourish. They also reveal the mind behind the lines. He thought in modular problems. Solve power transmission, then solve aiming, then solve protection. That sequence is the backbone of modern design. Finally, there is the human aftertaste. Some pages stayed hidden for generations. Some notes were lost or scattered. The messy path from sketchbook to battlefield meant that credit and danger moved separately. Ideas survived. People did not always. The designs remain as a record of a mind intent on shaping force. Hypatia. She taught geometry the way others taught prayers. In a workshop of brass and wood, she tuned instruments that read the sky and fixed a course. The plain astrolabe was simple in idea and powerful in use. A marked disc and an adjustable arm let a user sight a star and read its altitude. That number turns into latitude and time. And with enough readings, you find where you are on the sea. Her hands and her students kept tables and corrected older models. She is credited with editing and explaining complex texts that otherwise would have been lost. Those edits mattered because navigation depends on good numbers and reliable instruments. Sailors with better sights cross farther, traders find new routes, and empires gain reach. Geometry also helps aiming. Fortification makers and gunners use the same math to set angles for walls and for throwing machines. Knowing where a projectile will land comes down to measurement and careful calculation. The techniques she taught moved from classrooms into workshops that built better sights and more accurate bearings. We do not have most of her books. The manuscripts vanished or were scattered, and the city that kept them turned violent. Her death was public and brutal, and the shock shredded the network that passed on her notes. That absence is itself a kind of weapon. When a teacher is erased, the chain of craft can be broken. So the technology survives in fragments, while a human mind that shaped it becomes a shadow in later histories. Her instruments did not vanish with her. They lived on in margins and copies, and in the hands of students who carried rules across the Mediterranean. Arabic scholars translated and improved the same tables and citing tools. Centuries later, those improved instruments found their way into seafaring workshops. Sailors learned to measure altitude and to keep a steady course out of sight of land. That practical skill changed everything. A reliable sight lets a navigator dead reckon less and steer straighter. It also helps a builder set a wall at the right angle. Siege engineers used the same sighting ideas when they laid out battering rams and when gunners tuned their aim. Geometry moved from theory into timber and metal. Surviving commentaries show the chain. Notebooks from later centuries preserve equations and construction notes that echo the classroom methods once taught in Alexandria. That is proof that the work mattered. The technology traveled even when the original books did not. Then there is the cost. A scholar, torn from her circle, leaves more than missing pages. Networks of apprenticeship collapse. Workshops lose practical teachers. Knowledge fragments into recipes and lucky accidents rather than a continuous craft. When violence interrupts transmission, the result is not only cultural sorrow, it is slower technological progress. So the record that remains is a mixture of clever instruments and human absence. The instruments shaped voyages and walls and aim. The person who sharpened the tools was erased from the chain. That disappearance is itself part of the story of ancient weapons technology. Hard evidence sits beside a human shadow. Galileo Galilei. You lift a small brass tube to your eye, and the sky rearranges itself. He took an early instrument and pushed it until distant moons and mountains on the moon appeared as facts, not fables. His scope magnified objects 8 times at first, and then better models improved what sailors and soldiers could see. He did more than stare at stars. He carved an instrument that acted like a pocket engineer for gunners and builders. The geometric and military compass could scale maps, set proportions, and help calculate the right angle for a cannon. It could estimate the charge needed for different-sized balls and barrels. He sold 100 of these tools and taught men how to use them. The practical effect was immediate. A telescope lets a commander spot an enemy fleet before it rounds the headland. A reliable compass lets an artillery crew set a more accurate elevation faster than trial and error. That lowers wasted shots and gives an edge in both defense and attack. Workshops copied the methods and fortresses adapted the new measurements. Then the politics closed in. He clashed with powerful institutions that saw his findings as threats to accepted order. Trials and censures limited his public voice, and some of his writings were suppressed for years. That did not stop shipwrights and gunners from using better sights. But the voice that explained and taught was weakened. The lesson here is sharp. Tools spread even when the maker is muzzled. Yet, when a teacher is silenced, the chain of instruction frays. Technical advantage moves into practice, while human credit and nuance can be lost to history. His instruments left the bench and walked into workshops and shipyards. Craftsmen copied scales and proportional lines and built tools that did not need a scholar next to them. Gun crews used calibrated sights and learned to change elevation with fewer wasted shots. Ship captains used improved lenses and spotting methods to see a sail before it rounded a headland. The compass he sold came with manuals and demonstrations. That mattered because a tool that is sold and taught spreads faster than a book hidden on a shelf. Soldiers could measure angles, and crews could calculate charges without waiting for trial and error. That made artillery less a game of luck and more a repeatable skill. Fortresses could be laid out with truer angles. Walls and guns learned to fit one another. Practical adoption also shows in surviving inventories and in recipes passed down by gunners who never read academic treatises. Workmen noted proportions and notch placements, and then passed the same notes to apprentices. That chain of craft is how an inventor's idea becomes a standard method. But the human voice that explained the reasoning became fractured. Official pressure and a campaign to silence uncomfortable ideas narrowed public teaching. Some manuscripts were suppressed, some courses disappeared. The machines and the methods kept moving. The teacher, who made the instruction clear, did not always survive the battle over truth. The result is durable tools and fragile memory. Instruments that sharpened aim and sight, kept changing war and travel. The person who taught the how and why faded from common telling. That gap between tool and teacher is itself a kind of disappearance. Isaac Newton. A cannonball leaves the muzzle and the world becomes predictable. He gave us the rules that let engineers turn a guess into a table. The first law says objects keep doing what they are doing unless a force changes them. The second law links how hard you push to how fast something speeds up. The third law says every action has an equal and opposite reaction. Gravity ties it all together with a steady pull. Those simple rules let people model a flight. You can measure an initial speed and an angle, and then predict where the shot will land. That is why measurement mattered. Benjamin Robbins and others later built devices to catch bullets and read their speeds. The ballistic pendulum is a clever tool. It measures impact, and so gives away to no velocity without fancy clocks. That led to better firing tables. Firing tables change battle. An artillery crew that uses a table spends less time guessing. Elevation settings and charge amounts move from trial and error into repeatable procedures. Artillery becomes a predictable arm of the commander instead of a loud lottery. Fortification designers use the same math when they set slopes and thicknesses against expected hits. There is also air resistance and spin to consider. Those forces complicate the pure math, but the same approach lets engineers correct for them. That is how smoothed math moved into workshop notes and then into standard practice among gunners. The net effect is clear. Newton turned motion into a language that artisans and soldiers could use. The abstract law became a practical tool and reshaped how wars were planned. The result is weapons that hit where they are aimed and a new relationship between theory and force. The flight of a cannonball became a chartable path. Men measured speed with devices like the ballistic pendulum and then turned those numbers into tables that any gun crew could use. Those tables reduced guesswork. They told a crew how high to tilt the piece and how much powder to use for a given shot. That is why measurement mattered as much as theory. Engineers learned to correct for wind and for spinning projectiles. Air drags and small twists change where a shot lands. The same Newtonian logic lets you add correction factors and then fold them into a routine. A training crew practices a setting once and repeats it. The result is consistency across fields and navies. When methods become routine, they also become teachable. Manuals and workbench notes circulated among gunners and foundry workers. Apprentices copied notch placements and charge recipes in plain language. That is how an abstract law became a craft that an untrained soldier could apply under pressure. At the same time, states began to institutionalize the work. Ordnance bureaus gathered measurements, standardized calibers, and built firing tables for entire armies. Knowledge moved from the lone scholar to organized teams with laboratories and archives. That professionalization improved accuracy, but also concentrated control of the methods. One odd outcome is that many practical innovators vanish from the story. The man who measures and the crew who refines a method rarely get the credit that the theory receives. Yet it is their hand that turns equations into reliable effects on a battlefield. Tools and tables survive. People and their personal stories often do not. That gap matters. The history of weapons is as much about instruments and workshops as it is about great ideas. When the makers are missing, the record is incomplete, and power looks cleaner than it was in life. Antoine Lavoisier. He turned fire into a clear process you could measure. Before him, people talked about a lost substance called phlogiston. He showed that burning is not losing something. It is combining with a part of air that he named oxygen. That idea sounds tidy. In practice, it rewired chemistry and how people made things that burn. He did not stop at theory. He applied the new chemistry to the messy business of gunpowder. As a commissioner of powder, he tested raw materials and insisted on cleaner saltpeter, purer sulfur, and steadier charcoal. He changed how the ingredients were ground and how the grains were sized. Those steps make powder burn more evenly and more powerfully. In short, his lab work turned unpredictable blasts into repeatable force. Armies notice repeatable force. Cannons that use more consistent powder shoot truer and hit harder. That improves range and reduces wasted shot. Workshops copied his methods. Records from the period show inventories and factory notes shifting toward purer materials and better granulation. Those are small changes that add up to real battlefield advantage. Then politics intervened. His ties to finance and his role in public institutions made him a target in a violent year. The man who taught nations to measure combustion was removed in a public and final way. Papers were scattered, and some projects lost their champion. The practical methods survived in workshops and manuals. The voice that explained the science was harder to find. That quiet loss is as important as any broken manuscript. When a teacher disappears, the steady work of improvement can stumble. The technology keeps moving, but the record and the human face behind it can fade into shadow. His methods spread from royal workshops into ordinary powder houses. Craftsmen copied purification steps and the new granulation patterns. They kept notes that read like recipes. Clean saltpeter, stable charcoal, and careful milling became standard. That meant fewer misfires and more predictable blasts. Armies noticed the difference. Better powder made fortresses less safe and siegecraft more deadly. Training followed the tools. Makers taught apprentices to test grain size and to store batches in ways that reduced damp and spoilage. Manuals circulated in plain language. The work moved out of elite labs and into hands that could scale production. That shift turned a laboratory insight into an industrial advantage. Political life, however, was cruel to innovators. In a time of revolution, the scientist who had fixed a science found his name tied to the old order. He faced a public trial and a final punishment that silenced him forever. After that event, some of his papers were scattered, and some projects lost their steward. The machines and recipes carried on, but the teacher who had explained the why no longer spoke. This pattern repeats. Technical methods survive in guild notes and field manuals. Human voices and their subtler arguments do not always survive the same way. The practical work continued to improve explosives and firearms, even as the record of who pushed the changes became murkier. So, the real story is two-sided. On one hand, chemistry moved from mystery into measurement, and that changed war. On the other hand, the people who made those changes sometimes disappeared from history through politics or neglect. That disappearance is not just poetic. It shapes which innovations get credit and which are remembered as anonymous progress. The next chapters follow the same dangerous pattern. Tools persist. Names sometimes vanish. Alfred Nobel. A single idea turned a deadly liquid into a tool you could handle without fear. Before that, nitroglycerin was powerful and unstable. A jar could explode if you bumped it. The breakthrough was to soak the liquid into a porous mineral, so it would not detonate on a careless shock. Then, a controlled blasting cap would set it off when and where you wanted. That practical trick changed everything. Mines and tunnels that once took months to carve could be opened in weeks. Canals and railways carved through mountains with less human cost. The new explosive is easier to ship and to use in civil projects. At the same time, the same properties make it simple to use in warfare. Breaching walls and destroying bridges became faster and more efficient. He also invented a reliable detonator that let small initiators create predictable blasts. That combination of stable explosive and reliable ignition moved blasting from craft to industry. Workshops adopted recipes, foremen trained crews, and manuals replaced guesswork. The result was scale. Construction projects grew larger and faster. Then, life supplied a moral test. A tragic factory blast killed a close family member and raised public fear about the dangers in the work. The weaponized uses of the invention put the inventor in a strange place. He saw his creation used for harm as well as for good. That tension pushed him to leave instructions and funds in a will to reward peace and science rather than arms. The technical triumph is obvious. The moral aftertaste is more complicated. A single clever fix can build canals and also wreck fortresses. The story shows how invention moves fast and how the human story that follows can be messy and unresolved. The world learned to handle force without fear. Workshops refined the method and manuals circulated. Foremen set rules for storage and transport, and crews trained in timed blasts and safe distances. That predictability turned one-site projects into national undertakings. Canals cut through mountain ranges, railways punched through ridges. City plans changed because engineers could shape rock with controlled explosions instead of months of manual labor. At the same time, armies and rebels noticed the same ease of use. A stable explosive that travels well is also simple to deploy against fortifications and infrastructure. Governments adapted the formula to large-scale breaching. Insurgent groups used it to sabotage bridges and tracks. The invention shortened the time between idea and application. The inventor watched and wrestled with the result. He saw his tool used in both building and breaking. He saw it in construction crews and in violent headlines. That contradiction haunted him. He chose to redirect his legacy by funding prizes that celebrated peace and science. The move reads like an attempt to nudge history toward the good his work enabled rather than the harm. The pattern repeats across technology. A clever fix scales fast. Manuals and factory notes spread it. Practice standardizes it. The public story is messy. People who make things safe and useful often vanish into footnotes, while the results reshape societies. What remains is a paradox. A single practical idea can free labor and expand nations. The same idea can also make destruction easier and more efficient. Remembering both sides means remembering the tools and the people who lived with the consequences. J. Thomson. You look into a dark glass tube, and a pale glow crawls along a path when you flick a switch. He aimed beams of those glowing rays across a tube and bent them with magnets and plates. The beam moved like a school of fish, and the bend told him something important. The rays were not a kind of light. They were tiny particles that carried negative charge. He measured how much the particles bent and how strong the fields were. From that, he worked out a ratio of charge to mass. The number was tiny. It meant the particles were far lighter than any known atom. The conclusion was shattering. Atoms were not indivisible after all. They had parts. To make sense of the new pieces, he proposed a picture where many small negative parts sit inside a diffuse positive mass. Later work would change that image, but the real triumph was method. He showed that a careful experiment could pry open the atom and turn mystery into measurement. That new ability to see and measure the parts of matter rewired physics. It opened a path toward technologies that would use subatomic structure. It gave later scientists the tools to think about splitting nuclei and releasing enormous energy. For now, the simple fact mattered most. A tiny charged particle existed and could be controlled in a lab. The discovery was experimental craftsmanship. It also marked a turning point. Small things revealed big possibilities, and the road from curiosity to powerful application had begun. The beam did more than change a textbook. It changed how scientists thought about control. Once particles could be steered with fields and measured for charge and mass, experimenters built tools to sort and manipulate matter. Devices that trapped charged particles and measured their behavior became routine in labs. That practical skill let researchers probe deeper than surface chemistry and into the heart of the atom. A popular picture for the new atom placed tiny negative pieces inside a diffuse positive cloud. It helped people work with the idea, even though later experiments would replace it. The real achievement was method. Careful measurement turned a ghostly glow into numbers you could compare and repeat. Those numbers made the next steps possible. When scientists began to scatter particles off thin foils, they discovered a concentrated mass at the center of an atom. The nucleus did not fit the earlier picture. It forced a new model and a new set of experiments that measured nuclear charge and mass directly. Each experimental step added a bit more control. Control of subatomic particles opened doors. Physicists learned how to accelerate particles, how to strip electrons, and how to concentrate energy in very small spaces. Those capabilities fed ideas about releasing energy stored in the nucleus. The notion that atomic structure could yield vast energy was no longer pure speculation. It was a direction that experiment and engineering could follow. It is important to be clear. The discovery of tiny charged particles did not by itself create weapons. It created a toolbox and a language. That toolbox let later generations ask different questions and try different experiments. Some of those experiments led to the peaceful uses of atomic power. Others led to devastating weapons. The pattern repeats in science. A precise measurement and a clever apparatus turn a mystery into a technology. The path from curiosity to application can branch toward construction or destruction. The choice that follows belongs to people and institutions, not to the particle itself. J. Robert Oppenheimer. He walked into a desert laboratory and had to pull together the impossible. Generals wanted results. Politicians wanted speed. He gathered physicists, chemists, engineers, and draftsmen, and put them under one roof. They came from universities and hidden labs. They argued over equations and sleep schedules, and the moral cost of what they were making. He was more conductor than lone genius. His job was to turn scattered brilliance into a single, working program. That meant organizing work into manageable pieces. It meant settling arguments without crushing creativity. It meant keeping secrecy while feeding a team that needed coffee and confidence. He spoke to ministers and to boys in the shop with the same steady voice. The project had two awkward ironies. First, the science was new and fragile. Experiments failed and had to be repeated. Second, the timetable was ruthless. The war set the calendar, and every delay felt like a risk to lives. He moved people and equipment across the country in secrecy and improvised solutions under pressure. Then came the test in the desert. For months, men built devices and rehearsed measurement. On the morning the device would be tried, tables of instruments waited on nearby hills. They did not know how loud the world would be, or how an idea in a notebook would look when it burned bright in the sky. The first detonation was both scientific triumph and a moral rupture. Some who watched later remembered a hush that did not belong to victory alone. He later quoted an ancient line about becoming a destroyer. That line tells you the psychological weight that followed the bright flash. J. Robert Oppenheimer. After the flash, the desert held a strange silence, and then a long, stunned applause. He watched instruments and men and the sky itself change. The team had done what science promised. They had turned math and material into a new kind of force. But the moment carried a weight he could not shake. He spoke afterward with the voice of a man who had seen more than an experiment. He quoted an ancient line about becoming a destroyer of worlds. That was not a sound bite. It was a way to name the moral rupture he felt. For many of his colleagues, the work was necessity. For others, it became a burden that would not lift. In the years after the war, his public position shifted. He advised presidents and sat on panels, but political tides changed. Cold tensions turned scrutiny into suspicion. A security hearing in 1954 questioned loyalties and associations that had been tolerated during a desperate war. The outcome removed his security clearance and narrowed his official role. That removal is important. It is not the same as being physically erased. It is the quieter disappearance of voice and authority. People who once asked him for counsel no longer did. His ideas about control and caution had less sway inside the rooms that mattered. The pattern matters beyond one man. Societies build, and then sometimes unbuild, trusted voices when fear and politics press in. The person who led the making of a terrible tool can end up sidelined when the same tool reshapes global power. The history that remains is uneven. Instruments and tests survive in record. Human authority can be fragile and sometimes missing when we most need it. Lisa Meitner. A small puzzle in a chemistry lab led her to a conclusion that changed everything. Chemists had bombarded uranium with neutrons and found new lighter elements where none should be. The pieces did not fit known reactions. She and a nephew worked through the physics and saw the only way to make the numbers add up. She realized that a single uranium nucleus could split into two smaller nuclei, and that the missing mass turned into energy. Using a simple one-line calculation based on Einstein, she showed the energy per split is enormous compared with ordinary chemical reactions. That calculation turned a strange chemistry result into the idea of chain reactions and massive energy release. The moment was both theoretical and practical. Experimentalists provided confusing fragments and measurements. She provided the interpretation that made sense of the fragments and pointed toward potential consequences. That theoretical clarity transformed curiosity into a technology path that others would follow. Her reaction to the possible uses was immediate and public. She refused to take part in weapon development and later said plainly, "I will have nothing to do with a bomb." That refusal marked her as a scientist who drew a line between knowledge and action. Even so, recognition did not follow evenly. The experimenter received a top prize, while the theorist who supplied the critical explanation was left out. That omission became a lasting controversy, and a lesson about how credit and memory are assigned after powerful discoveries. This half ends with a sharp fact. She gave the key insight that turned experiment into energy. She also chose not to ride the train that insight opened toward weapons. The next part explains the technical follow-up and the longer legacy she left behind. Lisa Meitner. The calculation showed what the fragments alone could not. It made clear that mass disappears in the split and shows up as energy in amounts far larger than any chemical reaction can produce. That realization is what turns odd chemistry into a power source and into a weapon design path. When lab results arrived from collaborators, she worked through the physics and supplied the missing interpretation. Experimental fragments became a coherent picture. The physics pointed to a chain reaction that could run away if arranged in the right way. Others would take that path. She would not. She publicly refused to join weapon projects and said plainly she would have nothing to do with a bomb. That moral stance separated her from many who stayed and from the programs that followed. The irony is sharp. The critical explanation carried forward into technologies she rejected. Recognition did not follow her decision evenly. The major prize for the experimental finding went to the chemist, while the theorist who explained the mechanism remained on the margins of the official account. That omission has been debated for decades and is still cited as an example of how credit and memory can be skewed by circumstance and by who accepts what roles. Her legacy is complicated and important. The insight she supplied opened a route to both reactors and bombs. Her refusal to participate gives the story a moral contour that the technical data alone does not provide. The thing she explained is part of modern life in both hopeful and terrible ways. The person who warned and declined is both honored and, in some histories, noticeably missing. The chapter closes on that tension between human choice and technological consequence.